Okay, moving charges and magnetism. This video is about question solving and formula application. Let's go to the first question here. Eight wires. Cut the page perpendicular to point shown. Each wire carries current I naught. Odd currents are out of the page. And even currents into the page. Find the line integral B dot dl along the loop. The diagram is shown. This is a closed loop. There is 8 going in, 5 odd, so coming out, 2 even, so coming in, 4 even, so coming in, and there are outside number 1, 3, 6, and 7. This is the diagram here. They're asking, there are 8 wires cutting through the page perpendicularly, and each of the wire is carrying some current. Now they are asking finally to find what is BDL integral value, where we know that according to Ampere's circuital law, integral of B dot dl is equals to mu naught times I enclosed, and I enclosed, we find that let's say I enclosed, which is equals to, we do not consider the outside currents, we only consider the inside currents, so I8 plus I2 plus I4 minus I5. This is the total current, and since all of the values are same, I enclosed, which is equals to I naught plus I naught plus I naught minus I naught is equals to 2 I naught. Then integral B dot dl is equals to mu naught times I enclosed, which is equals to 2 mu naught I naught. This is the final answer. Now let's go to the next question. Find B due to a straight conductor of length 16 centimeter carrying 5 ampere of current at a distance of 6 centimeter from the midpoint of the conductor. Now we know the formula is basically, let's draw the diagram first. They're asking, they're saying there is a straight conductor which is of some length, that is I believe 16 centimeter length. There is a 5 ampere current and there is a point from midpoint of this midpoint of this conductor, or the distance is 6 centimeter. Now at this point, which we'll call it as P, what is the magnetic field? Bp, which is equals to, now we know the formula, we can write it as this angle which will get to be around 10 centimeters if we take 8 Pythagorean theorem. This is the diagram here. This is angle theta. This is also angle theta. Now the formula for P, which is equals to mu naught I by 4 pi r sine theta, or sine alpha plus sine beta, but since both are theta here, we will take it as sine theta as well, where sine theta, which is equals to P by H, which in case of here is P, which is 8 centimeter, and hypotenuse, which is 10 centimeter, which is equals to 4s are 5s are, so sine theta, which is equals to 4 by 5. Now substitute the values in the equation, where B equals mu naught, which is 4 pi 10 power into 10 power 7 minus 7 by 4 pi into, I believe the current was 5 ampere, 5 by the distance, which is 6 centimeter from the midpoint, 6 into 10 power minus 2, since it's in centimeter, with 2 sine theta, 2 times 4 by 5. When we solve this, we will get B, which is equals to 10 power minus 5 times 5 times 8 by 5, and into 1 by 6, and this we can write it as 2 3s are 2 4s are So it is B, which is equals to 4 by 3 into 10 power minus 5 Tesla, or B, which is equals to 40 by 3 micro Tesla. Let's go to the next question. If a straight conductor of length 40 centimeter is bent into form of a square, then find the magnetic induction, then B at center of square is. They gave 2 ampere current is passing through the conductor. Okay, there is a square. There is current 2 ampere passing through it, and there is a center magnetic field at the center, where if we take a single segment 4 by 4 by 4, so 10 centimeter is the single segment length, and if we take now, let's this angle we know should be 45-degree, same for this one, and this length should be L by 2 or 5 centimeter, and same for all the segments. So solution B in due to single segment, which is equals to mu naught by 4 pi I by R sine alpha plus beta, here sine 2 sine 45-degree. Now since due to all segments it will be B net at center will be equal to 4 times mu naught by 4 pi into I by R 2 sine 45-degree. Now when we substitute the values, we will get 4 into 10 power minus 7 into 2 ampere by R value should be L by 5, L by 2, so 5 centimeter, or 5 into 10 power minus 2, and 2 sine theta sine 45 is 2 times of root 2, which we can write it as, which we can rationalize by multiplying with root 2. We will get it as 8 root 2 by 5 into 10 power 10 power minus 5, that is Tesla. Now let's go to the next question. If a thin uniform wire of length 1 meter is bent into an equilateral triangle and carries a current of root 3 ampere in anti-clockwise direction, then find net magnetic induction, find B at the centroid or the center. Solution, the diagram is like this. This is the direction of current. Now there's a centroid. Now here the angle, since the total angle is 60°, here also if it is 30°, then this will become 60. This will also become 60 degrees. This distance, let's call it as r, and for this centroid, this distance from the center, we know it should be a by 2 root 3, and the side length, which is a, should be equal to 1 by 3 meter. Now same way as the before question where we find the magnetic field due to individual segment, and or add all the magnetic fields due to all individual segments, which is B equals mu naught by 4 pi I by r to sine 60°, and when we substitute, we will be net, which is equals to 3 times 3 into 10 power minus 7 into root 3 by r should be, when we substitute, it will be 1 by 6 root 3 into 10 power minus 2. Wait, no, there's no 10 power minus 2 here because it's already in meter. Now sine 60, which is equals to 2 times root 3 by 2, B net, which is equals to 3 times 6 root 3 times root 3 times root 3 again times 10 power minus 7. B at center is equals to 6 3s are 18 times 3 root 3 into 10 power minus 7, which is 5.4 root 3 micro Tesla. Which is the final answer. Now the next question is, a large straight current carrying conductor is bent in form of L shape. Find magnetic field at point P. I'll show the diagram. This is the bent conductor. This is the direction of current. This is P here, where they mentioned that this is A and this is also A, and the angles formed are theta 1 and theta 2. And this is the axis, this is y, this is x. Now solution for this question is, where we can say this angle here, which is equals to 90 minus theta 2, and this angle here 90 minus theta 1. And since there are two different angles here, B net at P, which is equals to B1 plus B2. So let's find B1, which is equals to mu naught by 4 pi I by R, and here sine 90 minus theta 1 plus sine 90 degree. is equals to, okay, let's find B2 as well first. Mu naught by 4 pi I by R sine 90 minus theta 2 plus sine 90 degree. This is B2. Now total B naught value, we will get it as, both we take common, this part we take common, mu naught by 4 pi I by R, as both is same, or we can take it as A, and we know sine 90 minus theta 1, which is equals to cos theta 1, and sine 90 minus theta 2 cos theta 2, and sine 90 value is 1. So both if we add, we will get cos theta 1 plus cos theta 2 plus 2. And if this is kind of the answer when theta 1 and theta 2 are different, but if cos theta 1 is equal to cos theta 2, is equals to 1 by root 2, assuming that theta 1 and theta 2 are 45 degrees here, then cos 45 degrees 1 by root 2, and substituting that, we will get B naught, which is equals to, B which is equal to mu naught by 4 pi I by R, or I by A, cos 45, which is 2 by root 2, or which we can write it as root 2 plus 2. This is the final answer for when theta equals 45 degree. Now let's go to next question. Infinite number of straight wires each carrying current I are equally placed as shown in the figure, which I will draw. Adjacent wires have current in opposite direction. Now find B at point P. Now there's a diagram here where This is point P, this is distance A, all is A, and here this angle is 30 degree, this is also 30 degree, and the current is going in this direction for these wires and in this direction for adjacent in wires. Adjacent wires will have opposite current direction, and this goes on for infinity. Now the formula is same, where B net, which is equals to mu naught by 4 pi I sine 2 sine 30 degrees, where distance is this, and d total, if we take this is a formula, but t total, wait, d total is not here, it will be d total, since currents are in opposite direction, it will be 1 by d minus 1 by 2d plus 1 by 3d minus 1 by 4d, and so on. And B net value finally, which is equals to mu naught I by two root 3 pi times A 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, and so on. Let's go to the next question. Find the magnetic field at P due to arrangement shown. This is the arrangement, 90 degrees. Current is going like this. This is a point P where this angle is 45 degrees, meaning this angle is 135 degrees, and this distance is d. Now the total magnetic field due to this will be V net, which is equals to 2 times mu naught I by 4 pi r sine 90 degrees plus sine of 180 minus, but somehow we got the answer as minus sine 45 degrees. And d value, r value, which is d by root 2, substituting in the equation, we will get b net value, which is equals to mu naught I by root 2 pi times d 1 minus 1 by root 2. Now next question, a pair of stationary and infinitely long bent wires are placed in the xy plane as shown. The wires carry 10 ampere current each. Let's draw the diagram first. This is L, P, I. This is Q and M. The segment L and M are along the x-axis and P and Q are along the y-axis, such that OS, this is O, this is S, and this is R. OS, which is equals to OR, equal to 0.02 meter. Find the magnitude and direction of the magnetic induction at the origin O. Now if we observe carefully, we will know the magnetic field on or at O due to L and M segments will be 0 because it is lying along the displacement vector, and it will only be due to this segment and this segment. It will not be due to this segment and this segment. Now considering that this distance was 0.2, we will get BSQ due to magnetic field due to this segment here, mu naught by 4 pi into I by OS, that is this distance here, which we will get 10 by 0.02, that is into 10 power minus 7. And BRP, which we will get it to be mu naught by 4 pi into I by OR segment, which we will get to be again 10 by 0.02 into 10 power minus 7 Tesla. And this we will get it to be around, if we add both of them, B net, which is equals to, both are acting in the same direction. If we use the right hand thumb rule, at this point, due to this, it is this, and due to this as well, it will be in this direction coming out of the screen. So both in the same direction, we can add them both. So we'll get the net magnetic field as 2 times 10 by 0.02 into 10 power minus 7, where we can write ones are 0.01 as 10 into 10 power 2 into 10 power minus 7, which will be equal to 10 power minus 4 Tesla. Next question. An equilateral triangle of side length L formed from a wire of uniform resistance the current the magnetic field at center is this is current I, P, Q and R, center O, The current will be going like this. If we consider due to this segment solution, let's consider first segment PR, B PR, which is equals to mu naught by 4 pi 2I by R by 3, where two-thirds of the current will go through PR by R, and 2 sine 60 degree, where R will be equal to A by 2 root 3, which is L by 2 root 3, and finally BPR, which is equals to mu naught by 4 pi 2I by root 3 R. This is directed outside. I'll keep R as it is now. As for BPQR segment, which is equals to 2 times of mu naught I by 3 by 4 pi R 2 sine 60 degree. This is directed to mu naught by 4 pi R I 2 sine 60 degree pointed inside. Then both are of equal magnitude. B net, which is equals to B1 minus B2, where magnitude of B1, which is equals to magnitude of B2, but direction is opposite. Therefore, one is going inside and one is going outside. B net, which is equals to 0. Let's go to the next question. A non-planar loop of of wire carrying current I is shown in the figure, and each straight section of the loop is 2A. Find the direction of magnetic field at this point at point P. Now they gave the diagram something like this. This is the diagram here. These are the axes: x, y, and z. The point P is located at a 0 comma a. Solution: let's consider them as two different loops. One loop like this and one more loop like this, where current is going like this. And now if we take a resultant, we should take, if we name them as A, B, C, D, E, and F, B due to A, B, C, D, A will be along I direction, I cap, x axis, and due to A, F, E, B, A, basically if we take the direction of loop, we will get the direction of the magnetic field lines. This is kind of the right hand thumb rule, and due to AFEBA will be along Z axis, so K cap magnitude will be same as current passing through will be equal. And when we take the direction of the resultant magnetic field, then resultant, which is equals to resultant magnetic field, which through parallelogram of vector addition we will get 1 by root 2 I cap plus K cap. Now let's go to the next question. They're saying a 2 ampere current is flowing through a circular coil of radius 10 centimeter containing 100 turns. Find magnetic flux density, that is magnetic field at center of coil. We know the formula to be around B center, which is equals to n mu naught I by 2r, so which is number of turns 100. Mu naught is 4 pi into 10 power minus 7. Current flowing through is 2 ampere by 2 times of a radius, which is 10 centimeter, 10 into 10 power minus 2, which we will get finally. Ones are, twos are, 1. So it will be 2 pi into 10 power minus 4 into 2, which is 4 pi into 10 power minus 4, which we can write it to be approximately 4 pi as 3.14, 12.6 into 10 power minus 4 Tesla, or 1.26 into 10 power, or 1.26 millitesla. Or we can write magnetic field unit as Weber per meter square, as Weber is unit for magnetic flux and meter square is area. Let's go to next question. A cell is connected between the points A and C. Okay, I will not describe the diagram. I'll just draw the diagram. This is 60-degree angle, and a cell is connected like this. This is O, this is A, this is C. Okay, I will read out the question. A cell is connected between points A and C of a circular conductor ABCD. A circular conductor of ABCD. This is D, this is B. If B1 and B2 are magnitudes of magnetic field at O due to currents ABC and ADC respectively, then ratio of B1 by B2 is. B1, which is B due to ABC, and B2 magnetic field due to ADC. Okay, now solution, they're asking find B1 by B2. Solution: magnetic field, which is equals to mu naught by 4 pi theta I by R, where B is directly proportional to theta I, where I1 by I2, which is inversely proportional to length, so which is equal to L1, L2 by L1, which is equals to theta 2 by theta 1. Now B1, which is equals to mu naught theta 1 I by 4 pi R by B2 is equals to mu naught theta 2 by I 4 pi R, where everything except theta 1 and theta 2 get cancelled. Wait, I are not common. I will also not get cancelled. This is I1 and I2, which will be equal to B1 by B2 is equals to theta 1 by theta 2 times I1 by I2, and from above relation where I1 by I2, which is equals to theta 2 by theta 1, B1 by B2, which is equals to theta 1 by theta 2 times theta 2 by theta 1, from relation B is equals to I theta I1 theta 1, B, which is equals to I2 theta 2, I1 theta 1, which is equal to I2 theta 2, I1 by I2, which is equals to theta 2 by theta 1. Based on this, we will get B1 by B2, which is always equal to 1 no matter the angle. Here where they gave it 60 degrees, but it does not matter. No matter the angle, it will always be 1. Now let's go to next question. Three rings, each having equal radius, are placed mutually perpendicular to each other and each having its center at the origin of coordinate system. If current I is flowing through each ring, then find the magnitude of magnetic field at the common center. Okay, there are three rings here. This is one ring. There is one more ring like this, and one more ring like this, where all are in individual axis. Now they're asking, this is the center O. They're asking magnitude. They're saying three rings of equal radius mutually perpendicular to each other. Then B center equal to how much? Now if we find BXY, the ring in the XY plane, XY meaning okay. Yes. The let's find first XY, the ring in the XY plane, which is this ring. This ring is in the XY plane. Wait. No. This ring is in the XY plane. Now BXY. Now if they said they did not clearly mention the direction of current, but we know that this due to this ring, an XY plane ring, the magnetic field should be acting along the Z direction, Z axis, which is the magnitude should be mu naught I by 2R along Z axis. And as for BYZ, which is also mu naught I by 2R along X axis, and BXZ or ZX is equals to mu naught I by 2R along Y axis. It's acting along all directions, this direction, as well as this direction. And it should be so B net vector should be equal to mu naught I by 2R I cap plus J cap plus K cap. And magnitude wise, which is equals to root 3 mu naught I by 2r. Now let's go to the next question. Two wires are wrapped over a wooden cylinder. To form two coaxial loops carrying currents I1 and I2. If I2, which is equals to 8I1, value of x for b equals 0 at the origin. O is, the diagram is this is, let's assume, a wooden surface. Now there are two loops like this. Two loops like this, and I1 and I2 opposite directions. Two wires are wrapped over a wooden cylinder from two coaxial loops having same axis. They are carrying currents I2 and I1. If I2 equals, okay, there is one more mention here. This distance is r and this whole distance is x. If I2, they gave I2 which is equals to 8I1. Then find the value for x for b equals 0 at origin. For if this is the origin, what should, and at here at origin b net which is equals to 0, then what should be the distance of x? Basically the distance of origin and the distance between origin and the second loop. And b net which is equals to single loop b I1 minus, or yes, b I2 is equals to 0. So actually b due to b axial due to circular loop, which is equals to mu naught I1 r square by 2r square plus x square whole power 3 by 2. And the radius of both is same. For let's name this as loop A and loop B. For loop A, the distance is also same. is r square b a, which is equals to mu naught I1 r square by 2 2 r square whole power 3 by 2, and b loop, which is equals to mu naught I 2 or 8 I1 r square by 2 times of r square plus x square whole power 3 by 2. Now if both should be equal, where BA minus BB, which is equals to 0, BA, which is equals to BB, loop B. So mu naught I1 r square by 2 times of 2r whole r square whole power 3 by 2, which is equals to mu naught 8I2 r square by 2 times of, this is I1 itself, not I2, r square plus x square whole power 3 by 2. Mu naught cancel, I1 cancel, r square cancel, 2 cancel. The remaining terms are 1 by 2r square whole power 3 by 2 is equals to 8 by r square plus x square whole power 3 by 2. By shifting it, we can write as r square plus x square whole power 3 by 2 is equals to 8 times of 2r square whole power 3 by 2. Now let's do cube root on both sides. We will get r square plus x square whole power 1 by 2 is equals to, cube root on both sides, we will get 2 2r square whole power 1 by 2, and square on both sides, we will get r square plus x square, which is equals to 4 2r square, where r square plus x square is equals to 8r square, and x square, which is equals to 7r square, x, which is equals to r root 7. This is the final answer. Let's go to the next question. Two wires wrapped over a conical frame form the loops 1 and 2 if they produce no net magnetic field at the apex P, find value of I1 by I2. There is a cone like this. That seems very weird. This is a cone. This is the apex P. This is the first loop. First loop, that is 1 having current I1 in this direction. This is the second loop, current in this direction I2 is having radius R2 here and R1 here. Okay, now let's find the solution. B net equals 0. B net, which is equals to B due to 1 minus B due to 2, which is equals to 0. Bi, which is equals to B2, and we saw in the previous question, B at axis of a circular loop, which is equals to mu naught R square by 2 times of R square plus X square whole power 3 by 2. This is the formula. And from a cone R square plus X square, which is equals to L square, that is slant height, L, and let's name it as B1, B2, right? B1, which is equal to mu naught I R square R1 square by 2 times of L cube slant height cube, which is, and we can write this as mu naught I R cube R1 cube by, or R1, this R1 by L whole cube by 2R1 and R by L, which is same as P by H, which is equals to sine theta, assuming this angle to be theta. So Bi is equals to mu naught by 2r1, mu naught I by 2r1 sine cube theta. B2 that became an oval. B2 is equals to mu naught I r square r2 square by L cube. Similar situation, we can write as B2, which is equals to mu naught I2 by 2r2 times sine cube theta, and we know both are equal, so we will get B1 equals B2. Equating both of them, we will get mu naught I1 by 2r1 sine cube theta, which is equals to mu naught I2 by 2r2 sine cube theta, sine cube theta, sine cube theta, mu naught, 2 cancel. So I1 by I2 is equals to R1 by R2. This is the final answer. If only if B1 equals B2 and they are opposite in nature. Now let's go to the next question. A thin insulated wire forms a spiral of n equals 100 turns, where I, which is equals to 8 milliampere, the inner and outer radius are equal to A, which is equals to 5 centimeter, and B is equals to 10 centimeter. Find B at center. Solution. Let's assume n, which is equals to number of turns per unit length, or number of turns per length, and let's assume the radius of ring is x and thickness of this ring is dx number of turns in ring is n times of dx, where n will be equal to n by b minus a. Magnetic field at center, which is equals to dB, will become mu naught, this is due to single, and dx I by 2x. So net field, we will integrate it, we will get it as b, which is equals to mu naught ni by 2 divided by integrated by 1 by x dx. Limits from a to b, which is equals to mu naught ni by 2 ln of b by a and finally we have the values of mu naught, n which is 100 turns, I which is 8 milliampere, and ln b by a, b which is 10 centimeter and a is 5 centimeter. If we substitute values, we will get and convert this into log 2.303 log of b by a. We will get final magnetic field answer to be approximately equal to 6.9 into 10 power minus 6 Tesla, or 6.9 micro Tesla. The diagram was given. The diagram was a spiral like this. A spiral of wire. Let's go to the next question. A plastic disc of radius r has a charge q uniformly distributed over its surface if the disc is rotated with a frequency f about its axis, then magnetic induction at the center is given by which solution They gave a plastic disc, maybe like a frisbee, which is having a radius of r, is rotated with a frequency f, then b at a at o is, they're asking. And there is a charge q distribution. Okay, let's, the magnetic field at center should be mu naught I by 2r, but let's take here as the magnetic field due to a single element, due to a single element mu naught I, which is di by 2r, or let's take 2x, a small segment, and let's assume dq, which is equals to q by pi r square 2 pi x with respect to dx for a small segment of the circumference, and di, which is equals to dq by t, or dq times f, di, which is equals to dq value, which is q by pi r square, unit area, charge per unit area per unit circumference, times f, and substituting this in the equation of dB, which is equals to d mu naught di by 2x, substituting this value here, dB, which is equals to mu naught by 2x q by pi r square, this is charge per unit area, times charge per unit circumference as well. That's why there's a dx here, and along with frequency we can write dB, which is equals to mu naught f by 2x q by pi r square times 2 pi r dx, and when we differentiate this we will get B, which is equals to mu naught F Q 2 pi r by 2 pi r square, and differentiation of 1 by x dx, we will get magnetic field at center of that disk, which is equals to mu naught q f times 2 pi r, 2 pi cancel, r cancel, this mu naught qf by r times ln of, I guess, just x, the small element x. Or wait a second. This, wait a second. Actually, this is not 2 pi r. This is not r, but this is 2 pi x dx and 2 pi x with respect to dx. Here as well, it's not r but x. So this r square will remain. It will be mu naught f q 2 pi x dx by 2x pi r square. Here 2 cancel, pi cancel, x cancel, and we'll get finally differentiation, which is equals to differentiation. When we differentiate, we will get all our constants except dx when it is 0 to r. Differentiating this, the differentiation integral, which will be from 0 to r. So we will have mu naught f q by r square, differentiation of dx from 0 to r. So it will be b, which is equals to mu naught f q by r square times r, where this will be a final equation, which is equals to mu naught f q by r. This is the net magnetic field at the center. Now let's go to the next question. The main important understanding of this question lying in taking dq value, where we took dq value as Where is dq value? Yes, dq value as q by pi r square times 2 pi x dx, where charge per unit area for unit 2 pi circumference times the small elements. Now let's see the next question. A charge of 1 coulomb is placed at one end of a non-conducting rod of length 0.6 meter. The rod is rotated in a vertical plane about a horizontal axis passing through the other end of the rod with angular frequency 10 power 4 pi radian per second. Find B at a point on axis of rotation at a distance of 0.8 meter from center of the circular path. Let's read the question again. A charge of 1 coulomb, it's a moving charge because they're rotating the non-conducting rod. A charge of 1 coulomb is placed at one end of a non-conducting rod of length 0.6 meter. Length of rod is 0.6 meter. And the rod is rotated in the vertical plane about a horizontal axis, passing through the other end of rod. Find the field at a point on the axis of rotation of 0.8 from center of circular path. Okay, I guess this is a rod. This is the axis of rotation. They are rotating this rod like this. Where there is a charge of 1 coulomb at one end of this rod, and the frequency is 10 power 4 pi radian per second. Then what is the magnetic field at 0.8 meter from the center, and the rod itself is 0.6 meter? Magnetic B field at E is equals to. Solution: B, which is equals to mu naught I r square. This is a basic equation for a circular loop. 2r square plus x square whole power 3 by 2, and here I we do not know, so I we need to find out. I, which equals to q by t, where t we can write it as, where omega equals 2 pi by t, t we can write it as 2 pi by omega, and based on that we will get I, which is equals to q omega by 2 pi, where omega, which is equals to q 10 power 4 pi by 2 pi, pi cancel, we will get I, which is equals to 5q 10 power 3 ampere, and charge is 1 coulomb, so it is 5 into 10 power 3 ampere. Which is a very large current, or did I make a mistake? Q omega by 2 pi. Omega they gave us 10 power 4 pi. 10 and 1 coulomb, so 5 into 10 power 3 ampere, and substituting current value, HB equals 4 pi into 10 power minus 7 into I, which is 5 into 10 power 3 into r square. They did not give the radius. They did not give the radius of the this rod. So I think we cannot solve this, or let's keep it as r square. I will see this question later. They did not give the radius, so I will just write the final equation. That we will get mu naught by 4 pi q omega r square by r square plus x square whole power 3 by 2. This is the equation, and then if we know the r value, we can substitute in this equation. When we solve, we will get the approximate value of magnetic field. Let's go to the next question. Two circular coils made of same material having radii 20 centimeter and 30 centimeter have turns 100 and 50 respectively if connected, if A, they are connected in series, B in parallel, separately across a source of EMF, basically connected to a battery. Find the ratio of B produced at center. Okay, this is a question why they are connected in series and they are connected in parallel, because the relation here between that is for finding out the current passing through the coils. If when we can calculate the amount of current passing through each coil, that is if yes, the current passing through each coil based on if they are connected in series and if they are not. And the resistance we can find as resistance is equals to rho L by A, where rho is common for both of the materials. Okay, in case of first case, in case of A, in series, in series case, we know current will remain constant. In case of parallel, so we don't need to calculate current. Both cases, current, both coils, current will be same. In parallel, current will not be same, but potential difference will be same. Okay, now let's go for first case. First case in series. Let's name each coils as coil A and B. Coil A, magnetic field due to coil A, let's call it as BAS, where coil A in series is equal to at center which is equals to mu naught I by IS by 2 times of R which is for the first coil is 20 centimeter, 2 times 0.2 meter, and BBS, which is the second coil, mu naught is by 2 times of 0.3. So BAS by BBS, which is what they asked us to find, will be mu naught, 2 cancel, is cancel. So it will be 0.3 by 0.2, which is basically 1.5. This is the first case. Wait a second, I seem to have forgotten about the turns here. There are, the first coil is 100 turns, so it's not 1.5, 150. So this is 100 turns into 100 into 50. So ones are, twos are, and it will be 0.3 into 2, 1.5 into 2. So it's not 1.5 but 3 is to 1. 3 is to 1 or 3 by 1. 3 by 1 is the first value. Now let's go for in parallel case. Parallel case where potential difference is same. Let's find resistance of A first. Resistance of A coil, which is equals to rho L by A, which we can write it as L, which is equals to 2 pi r, 2 pi small r A, which is radius, which is I believe 0.2, yes, 0.2, 0.2 by area pi r square, which is pi 0.2 into 0.2, pi cancel, ones are, tens are, so Ra, which is equals to 10 rho. Now let's find Rp. Wait a second, which is times 100 actually, because there are 100 turns, so it is 10 power 3 rho, and Rb, which is equals to rho times 50 times 2 pi times 0.3 by pi 0.3 times 0.3, which we will get Rb, which is equals to 100 rho by, or 1000 rho by 3, and potential difference is same, V, which is equals to Ia by Ia, Ra, which is equals to V, which is equals to IBRB, and Ra by Rb, which is equals to Ib by Ia, which we will get it as 1000 row by 1000 by 3 row, 1000 cancel, row cancel, and 3IA, which is equals to IB. This is a current relation. Now we know the current, so let's find magnetic field now. Magnetic field B, magnetic field BAP parallel of coil A of P of parallel, which is mu naught N, which is 100, or let's just write it. Let's just write magnetic field formula first. B center, which is equals to mu naught R, mu naught not R, mu naught I by 2R. Now BAP is equals to mu naught times 100 times IA by 2 times of resistance of A, which is 1000 row, and BBP, which is equals to mu naught 50 by 3 times of IA by 2, here 3000 row, division, mu naught cancel, 2 cancel, ones are twos are, IA cancel, 1000 row cancel. Now I'll get BAP by BBP is equals to 2 by 9. Now let's go to the next question. Okay, then the next question is, two circular coils are made from a uniform wire. The ratio of radius of coils is 2:3, and number of turns, ratio of number of turns is 3:4. If they are connected in parallel across a battery. First we should find A, find ratio of magnetic inductions, basically magnetic fields at their centers. B, ratio of magnetic moments of two coils. Okay, they gave that solution R1 by R2, which is equal to 2 is to 2 by 3, and N1 by N2 is equals to 3 by 4. So basically R1, which is equals to 2 by 3 R2, and N1, which is equals to 3 by 4 N2. They are connected in parallel. Now B naught R, which is equals to B center, which is equals to mu naught R by mu naught I by 2R, mu naught N into I by 2R. So B1 by B2, which is equals to mu naught I, which is V by R, V by R A. This is, let's take it as small r, resistance of A times N1 by 2R1 by mu naught V by RB times of N2 by 2R2, mu naught 2, mu naught 2 cancel, VV cancel, remaining is RA by RA yes it is RA N1 R2 by RB N2 into R1, where R1 by R2, where N1 by N2 was given already, which is RA by RB times N1 by N2, which we know is 3 by 4, times R1 by R2, which is 2 is to 3. We can write as 3 by 2, and we will get resistance. We can write it as rho L by A. So L for the first coil is number of terms 1 n1 times 2 pi r1 9 by 8 by area, that is pi r1 square rho n2 into 2 by r2. Rho cancel, 2 cancel, and we will get b1 by b2, which is equal to n1 r2 by n2 r1 times, before substituting it was, let's write it as it was before substituting, n1 by n2 r2 by r1, n1 by n2 r2 by r1. This is same as b1 by b2, which is equals to n1 by n2 whole square times r2 by r1 whole square. And if we substitute, we will get it as n1 by n2, which was 3 by 4 whole square times r2 by r1 3 by 2 whole square, 81 by, but I guess this might not be correct, so b1 by b2, which is equals to r2 by r1 whole square, which we will get 3 square by 4 square, not 4 square, 2 square, which you will get as 9 by 4. As for magnetic moment, which is equal to n times I times A, where I equals V by rho L times A, where area is common for both of them, as we are not considering area of coils but area of the cross section of wire. So M, which is equals to n times V by rho L times A, which we can write as nv rho, length will be equal to n times 2 pi r A, n and cancel. So m which is m1 by m2 is equals to V, which is common, V by rho, which is common, V by rho by V by rho cancel. Area is also common, so cancel. 1 by 2 pi r1 by 1 by 2 pi r2. 2 pi cancel, so it is r2 by r1. But it seems there is one more A here. This A, NIA, this A is the area of the coil, and this is a wire. This is coil. So it will be A times A coil. Then there should be one more pi r1 square here. R1 cancel, and pi r2 square here. So R2 cancel, pi cancel. So here we will not get R2 by R1, but R1 by R2. M1 by M2, which is equals to R1 by R2. Where M1 by M2, which is equals to R1 by R2, they gave it as 2:3. Okay, then that will be the end of this video.